Good morning. My name is Juan Soria. I am researcher of the Cabanilles Institute of Biodiversity and Evolutionary Ecology of the University of Valencia in Spain. I want to talk about the study of submerged aquatic vegetation using remote sensing imagery in Gallocanta Lake in Aragon, Spain. Gallocanta Lake is an endorheic saltwater lake. This specific type of wetland zone is currently rare in the Mediterranean biogeographical area of the Western Palearctic. It is considered unusual because the water level shows different seasonality and great period of fluctuation compared to other salt lakes. Also, is of relevant interest because it is considered as the best preserved in Western Europe. The Ramsar wetland area is about 90 square kilometers and the maximum lake area is over 10 square kilometers. The objectives of the study are monitoring the aquatic vegetation of Saline Gallocanta Lake with remote sensing from 2016 to 2020 year. Obtain the most appropriate vegetation index to apply to the study in this lake, to discover vegetation growth patterns and annual distribution in the lake, and evaluate the possible environmental factors that influence the growth and disappearance of vegetation.
Hello, my name is Miriam, and today I will talk about remote sensing in lakes. In recent decades, numerous water quality studies have been carried out using remote sensing. The European Union Copernicus program includes a series of satellites that provide high-quality, free-of-charge information. This study has been conducted using 6 vegetation indices that has been applied to Sentinel-2 satellite images. Sentinel-2 missions are satellite constellation for water quality, 2 at the present times, Sentinel-2A and Sentinel-2B. Images 219 kilometers wide, tiles 100 per 100 kilometers. Times revisits each one every 10 days. MSY sensor, 13 spectral bands in the beige, near and sweet, 10 meters, 20 meters and 16 meters spatial resolution, combined digital images taken by Sentinel-2A and 2B within 5 days frequency. About the submerged vegetation, aquatic vegetation is the most visual biological aspect in a swallowstone lake because under normal circumstances it covers most of the bottom boundary layer and its surrounding area. The presence of this vegetation is an indicator of the quality of the ecosystem. Its study is one of the variables used to evaluate ecological status according to the European Union's Water Framework Directive. Vegetation communities occur in space and time in response to water characteristics such as flood level, water quality, and mineralization. Remote sensing provides a visual study of the distribution vegetation in a time series in a complementary way to field work, allowing to know the spatial and temporal heterogeneity. It is possible to observe the evolution of the submerged aquatic vegetation and that of the peripheral wetland area, the colonization processes after the flood, at which time salinity is lower, and the disappearance of plants when the level drops and salinity increases.
Hello, my name is Samuel Morales and I'm going to start by talking about methods. First, we have obtained cloudless images of the European Space Agency's Copernicus program and resampled the pixel size to 10 meters. A mask has then been added to the contour of the lake and applied to it different vegetation indices and selected the most appropriate for the years 2016, 2019, and 2020. The indices used are the most popular NDVI Normalized Difference Vegetation Index that uses bands VA and V4, being its formula VA minus V4 divided between VA plus V4, and in a range of values between -1 and +1. The following is NDI 45 Normalized Difference Index, has the same formula but uses band 5, thus getting less saturation at higher values. ARBI has a higher resistance to atmospheric effects by multiplying the red band by 2 and adding the blue band to it. The NDVI Transform Normalized Difference Vegetation Index is the square root of the NDVI. It always has positive values and a higher coefficient of determination than NDVI. Next, MCARI Modified Chlorophyll Absorption Ratio Index is used to calculate chlorophyll concentration and uses red, green, and IR radiation bands. Finally, IPVI Infrared Percentage Vegetation Index is similar to the NDVI, but its range is positive.
And I will talk about the aquatic vegetation of the Gallocanta Lake. First, we have a schematic representation of the aquatic vegetation over the IB section of the Gallocanta Lake, which is divided into three parts: the nearshore, the intermediate swallow zone, and the deepest part of the swallow zone. Assuming that this section represents the absence of freshwater inflow into the zone of the lake, we can see that there's only a few species. Carafoetida appears on the surroundings of the lake. Lamprotamium papulosum has a wide distribution in the deepest part of the swallow zone, and it decreases as it approaches to the near shore. It's completely the opposite for Rupia drepanensis, which is all over the near shore and decreases as approaches to the deepest part, suggesting an interaction between these two species. And lastly, Rupia maritima, that can be found in the lake waters. Secondly, there's the deepest part of the lake, surrounded by the deepest part of the swallow zone. Here appears a new species, which is Caragalioides, with a spotty distribution. Carafoetida stays on the surroundings of the lake. Lamprotamium papulosum has a sparse distribution. Then is Rupia drepanensis in a isolated stance surrounded by other species. It's the same for Rupia maritima. Finally, we arrive to the CD section of the lake. In this section, we assume that there is a freshwater inflow to the lake. Due to this freshwater inflow exists a wide variety of species. Carafoetida appears on the surroundings. Caraispida and Groenlandia densa grow next to the freshwater inflow. Lamprotamium papulosum shows a more wide distribution on the deepest part of the swallow zone. Potamogetum pectinatus and Rupia chirrosa shows up next to the inflow of fresh water. Rupia drepanensis extends from the nearshore to the intermediate swallow zone. Rupia maritima has a scattered distribution over the lake. And finally, like other species I mentioned here, Thanicella palustris grows next to the freshwater inflow.
Here, we have made a comparison of the different vegetation indices on March 27, 2019 to choose the most appropriate for the research being NDI45. In 2016, we have chosen 6 images of the months January, April, May, June, November, and December, where the green color indicates the presence of vegetation and blue its absence. During the spring months is when there is the highest percentage, while summer and autumn have a very low level and a very high level of salinity. In 2019, the vegetation doesn't go away in any months. First, there is a clear evolution between January and July. The vegetation increases in the lake to reach its peak in June. Then, during the summer, it decreases, and in autumn there is a little. Finally, in winter, there is a small increase. In 2020, the situation explained with more underwater vegetation in the winter-summer seasons is repeated, but 2020 ends and 2021 begins, with a snowfall over the lake that causes its freezing.
And now I present the conclusions of our work. Remote sensing is a powerful tool to study the distribution of aquatic vegetation in shallow lakes. The best index in our case study, applied to Sentinel-2 imagery, is the normalized difference index between 4 and 5 bands, red band and red edge band. The normal evolution of submerged vegetation in Gallocanta Lake is to colonize after a drought period and disappear when the lake dries in hot summer or water frozen in cold winter, as seen in the images. Vegetation can cover all the bottom of the lake, indicating a good ecological status, but it's necessary the sampling of plants to know what is the better distribution. Now, next works are pointed to obtain field data to map the distribution of taxa when available and correlation with vegetation indices. And thank you very much for your attention, and that's all.